Hi, I'm Grace Fanson, and I'm an undergraduate physics student at Georgia Tech. Over the last year, I've been working on the project I'm about to present to you with Dr. James Ray and Dr. Francis Rivera Hernandez. And throughout the process, I've fallen in love with planetary science, and it's inspired me to pursue planetary science in graduate school. Without further ado, let's get into it. 70% of the surface of Mars has been resurfaced by basaltic volcanism. That level of resurfacing can't be accounted for by the volcanoes we've confirmed so far. There must be some other source of volcanic material. On Earth, we have something called a collapsed volcano, like Crater Lake in Oregon. These volcanoes used to be high in elevation, but have since fallen to elevations similar to the surrounding terrain. If it exists on Earth, it could exist on Mars too. Some candidate collapsed volcanoes have been identified in the Arabia-Terra region of Mars. For context, this is a topographical map of Mars from an instrument called MOLA. Red and white regions have the highest elevation, while blue regions have low elevation. Circled is the Arabia-Terra region. The first place to look for collapsed volcanoes is strangely shaped pateras. A patera is a depression in a planetary surface. It could be a lake, an impact crater, or in this case a caldera, which is the opening of a volcano. Most pateras on Mars are considered to be impact craters because most of them are. However, Eden Patera has been identified as a candidate collapsed volcano because it doesn't have some key impact crater qualities. For example, impact craters generally have impact ejecta, an uplifted rim, and nearly circular geometry. As you can see by this 3D model of Eden Patera, it does not share these qualities. Most of the inquiry so far has been focused on morphological studies. In my study, I investigated the immediate surroundings of Eden Patera. I did a spectroscopic and thermal inertia analysis of the area to determine if the minerals are consistent with volcanic activity. To start, I used data from the instrument called XRISM, which is a spectrometer on the Mars Reconnaissance Orbiter, to search for a mineral called silica. Silica is a common mineral found in volcanoes, and it has diagnostic absorption features in its spectrum that are visible within the range of wavelengths XRISM can measure. On this topographical map, you can see the available targeted XRISM images. Unfortunately, there are no images of Eden Patera itself, so we have to look at the surrounding region. On this map, I labeled the images where I could not find silica with a red X, the images where I did find silica with a blue circle, and images that were unavailable with a white X. It's not surprising that there are so many red X's because the Arabia-Terra region is very dusty, obscuring much of the land beneath from XRISM's view. This means detections we do see are very promising because we can see them despite the dust. I labeled the images where I found silica A through F. I'll use this notation in future slides when referencing data from a particular image. Let's zoom in on one XRISM image 200 kilometers from Eden Patera. On the left, we see a 3D model of the crater with a high-res image overlaid and the outline of the XRISM image overlaid as well. On the right, you can see the XRISM image with circles called regions of interest, or ROIs. Each of these ROIs are places where I located silica. On the upper right-hand side of the image, you'll see a maroon ROI. Here is its spectrum. It has characteristic absorptions of silica at 1.4, 1.9, and 2.2 microns. These features can tell us more than what mineral we're looking at, though. Based on the concavity of the absorption and the exact position of the minimum, we can learn more about how it was formed. Following the method of Pinot et al. 2020, I computed the concavity ratio criterion, or CRC, for each region of interest I found, and I plotted it against the position of the absorption feature. According to this graph, minerals plotted in the top half were formed during a hydrothermal process, while minerals plotted at the bottom were formed in a weathering process. Additionally, those plotted on the left-hand side are considered opal A, an amorphous silica, while those plotted on the right are considered opal CT, a crystalline silica. These regions were determined experimentally by Pinot. Most of my points are on the weathering and opal CT quadrant of the spectrum for the 1.9 absorption feature. Comparing my points to the known minerals measured by Pinot, we can see they are most consistent with undifferentiated bedrock, intracaldera light tone deposits, and alluvial fan and fan delta deposits. Now, taking a look at the same analysis of the 1.4 absorption spectra, we can see my data plot on the weathering half of the graph, but more spread between Opal A and Opal CT. Comparing this to Pinot's data still shows consistency with undifferentiated bedrock, intracaldera light tone deposits, and alluvial fan and fan delta deposits. It's not concerning that we see both crystalline and amorphous silica on these plots. It's likely that they exist in a mixture, but amorphous silica shows up more in the 1.4 feature than it does in the 1.9 feature. Comparing the two plots, we can see that Pinot's data shift from the Opal CT side to the Opal A side, just as mine do. It's unlikely my data fit with intracrater aeolian deposits because my points don't consistently plot within that region. The second part of my study was an analysis of the thermal inertia of these points as they relate to the morphology. This map here is the nighttime temperature divided by the daytime temperature. The entire surface bakes in the sun all day. When the sun goes down, the surface cools at different rates depending on the material. Materials that retain heat for longer are considered to have high thermal inertia, while those that cool off quickly are considered to have low thermal inertia. In red, we see high thermal inertia objects, while in blue we see low thermal inertia objects. Thermal inertia can help us understand particle size and what kind of material we are looking at. Light fluffy things, like volcanic ash, has low thermal inertia, while large, dense things like volcanic glass has high thermal inertia. I think this is intuitive. The map is a useful way to visualize this concept, but the quantitative method involves a more intrinsic quality of the material, like thermal conductivity, specific heat, and mass density. The instrument Themis can measure this value, and I use this data in the following analysis. Here, I have plotted the thermal inertia against longitude. Clearly, there's a negative slope to the east. Additionally, the values for thermal inertia are consistent with those of volcanic ash. It should be noted that high thermal inertia value to the west is close to the Moth Vallis region and could have formed during a different event. My preliminary interpretations are that there are minerals in the Arabia Terra region consistent with volcanic material. The thermal inertia analysis indicates that the locations observed have thermal inertias consistent with volcanic ash rather than volcanic glass. If there were indeed volcanoes in Arabia Terra, the thermal inertia values suggest they would have been explosive. We also see that thermal inertia falls with distance to the east. This is consistent with existing models that predict the ash to trend towards the east, getting thinner with distance. The decreased thermal inertia could be reflecting thinning ash. In the future, I'd like to incorporate higher coverage but lower spatial resolution CRISM images so I can fill in some gaps in my graphs. This will allow me to look at the mineralogy of Eden Patera itself. I would also like to incorporate this data with high-rise digital elevation models to connect spectroscopic trends with morphology. Thank you so much for watching this video. I've really enjoyed this project and I hope you have too. If you have any questions or you'd just like to learn a little bit more, feel free to email me at the email below. Thank you. Bye.